Welcome to Third Angle, where NanoVoxel redefines 3D printing. I'm your host, Paul Hames from industrial software company PTC. In this podcast, we share the moments where digital transforms physical and meet the brilliant minds behind some of the most innovative products around the world, each powered by PTC technology. Today, we're diving into the groundbreaking world of NanoVoxel, a company specializing in two-photon polymerization 3D printing technology, or in other words, 3D printing in miniature. They aim to transform micromanufacturing by replicating parts into silicon molds with unmatched precision. Our producer, Aaron, visited NanoVoxel's state-of-the-art facilities to meet founder Domenico Foglia. Hear how their incredible feats of micromanufacturing can create a Baby Yoda the size of a grain of sand or an entire castle crafted on a pencil tip.
I'm Domenico, I'm the founder of NanoVoxel. Today we are at the Tricor building. We are just outside the labs of NanoVoxel, and we are ready to show you a little bit of our story. Here we just stepped inside our main lab. There are the 3D printing machines. We have our laboratory, our microscopes, and this is where most of the magic is happening. You can see, for example, that here Nemanja is working on a CAD file. CAD software is a very important part of our work, because what we normally get from customers needs to be reworked. So the very first step of our work is to understand what the customer needs and to adapt it to our printing design and so on. So we call it designs for manufacturing, and very often we have to modify a little bit to adapt it to our manufacturing capabilities. And so the very first step normally is to analyze the part, modify it, and then create a so-called print file, which we can move to the next step of the printer. So we are moving more inside the lab. There is the laboratory. We have Rania working with it, and these are pretty advanced equipment, because we are working on a scale where standard microscope, for example, do not work anymore, and we had to invest quite good money to have instruments which are able to measure already what we are creating. Because at the moment, what Nemanja is doing is printing parts which are not visible. It's about 200 microns. Yeah, and this is what's very exciting here, is that we are doing stuff that no one else worldwide is able to do. Here we have, for example, two special microscopes. One is so-called metallographic microscope, because he has to come to a resolution where the grain size of metals is possible to recognize. So it's having already a very, very high resolution. While on the left side, and you can see this box is taken to create a airflow that dust is not coming on the parts. And on the left side, there is what we call the LSM, the laser scanning microscope, which is a special microscope which is using three different principles: confocal, laser, and white light interferometer, to make super high precision measurement and to create also a 3D scan of these microparts. And normally there are few microscopes which are able to create a three-dimensional measurement of transparent parts. This you can look inside the microscope, and this you can look on the screen. Here we have this one is a optical microscope. When you watch inside, you can see the microscale of the parts that we have created. Probably with naked eyes you just see a block, but if you look inside, you see how the microstructure it's looking like. It's very difficult for people to understand just the scale of the parts. We have printed, let's say, some small cases, like we have Baby Yodas, different scales. When people see the size of the Baby Yoda, which is smaller than 1 millimeter, this is like looking like a sand corn, people say, I can't believe that. We are now in front of our vacuum casting station, where 3D printing is the core of our technology, but actually one of our main competence is not only the 3D printing as a service, but also to replicate the incredible resolution, accuracy, and designs of freedom of 3D printing in other processes, so that we are able to create microparts also in other materials and at higher productivity. And for example, what Carolina just did is called vacuum casting, where basically by starting from a geometry which is called a master, we're able to replicate this part into others material like a silicon mold. And for example, these are kind of silicon molds. As you can see, they recreate the geometry. This is basically a negative of the print. And so after creating this silicon mold, we have a replication of what we've been able to do in 3D print. So what we do here, the core of our experience is inside this clean room. And this is the 2-photon polymerization machine. This machine is from the company UpNano, which actually is in the same building as us. It's our partner company. We do microfluidics, microneedles, micronozzles. We create microparts for mechanicals like microgears, or for example, there is a strong interest from different customers in terms of endoscopes, because they're getting smaller and smaller to be less invasive inside the body. What we do is when we have to run the machine, we have this clean room, but also that the parts that dress is also very important. So you can see Rania go inside and activate the machine. You can see the slide is opening, and now what we have to do is loading a substrate, which is this. It can be of 20 by 20 millimeters or 40 by 40 millimeters. Is a glass substrate, and is put on the top, and is immersed then in a photopolymer vat, kind of bath. So basically, we have liquid photopolymers, and when light is hitting it, it's polymerizing and hardened. Pixels are easy to interpret, but they are two-dimensional, so in X and Y. A voxel instead is a volumetrical pixel. So we have X, Y, and Z. And the incredible of this machine is that it's able to polymerize voxel of the size below 1 micrometer. So the maximal resolution that we have is 200 nanometers in X and Y and 500 nanometers in Z. And this is allowing incredible stuff. Like UpNano, for example, made a project of creating an entire castle on a pencil. You can see here. This is a pencil tip, which has been sharpened as much as possible. And this castle here, which resembles a real castle, is having feature size down to 2-3 microns. And the resolution is unbelievable, and you need a scanning electron microscope to see that, because otherwise there would be no chance to see with an optical microscope. Maybe you can watch on the screen. So, as you can see here on this printed picture, the feature size is going down to a few micrometers. For example, these columns here, they have a diameter of 5 to 6 micron. And I invite everyone to look on search engines about the castle on a pencil tip, because it's a very impressive project. We will go now to the other lab, because a very important part of our vertical integrated solution is also the micro-injection molding machine and micro-injection molding. Here we had also We're in front of the micropower injection molding machine of Wittmann, which is probably the most advanced micro-injection molding machine on the market. Martin is our expert of micro-manufacturing, micro-injection molding, and basically he had the idea and he implemented all the steps necessary to be able to make work in this machine. These are processes which are able via 3D printing to create soft or hard tools to then be able to use a micro-injection molding machine, which is the standard to create microparts in high volume. These machines can go to create, to produce up to 10 million parts per year, for example, and because they are super efficient, super fast, and of course they have a different scale than 3D printing. One of the most exciting things that we are doing in NanoVoxel is impacting the future life of the people. We are working on microneedles. We are working on new endoscopes, which can go maybe do analysis of veins because they are so small that they can fit inside that. They can go up to brains or inside the heart. Then I have a clear view of the impact that we are having in this world. Of course, we're not that credible yet because it's a tiny startup. We have to demonstrate people, and now we are exactly expanding, scaling up. We are in the middle of the go-to-market process, and we have the luck that we're a special startup because we do not need 5 years or 10 years to go to the market like a lot of medical devices companies do. So we are very enthusiastic about how the things are developing. We already found the next location here in Vienna because we will need more space for production.
That was Domenica from NanoVoxel guiding us through the world of micromanufacturing. Now it's time to meet our expert, John Hirschtick from PTC. John, we've heard about Onshape in previous episodes, but in this instance, NanoVoxel credits Onshape with facilitating collaboration and reducing 3D printing time with Boolean tools. Are you able to explain how this works to our listeners?
As you've heard, NanoVoxel is a leader in high-precision microparts using 2-photon polymerization, or 2PP, micro 3D printing technology. It combines advanced printing systems with micro injection molding and cavity manufacturing expertise. So all these come together to produce micro and nanometer resolution components. NanoVoxel, they needed a cloud-native, flexible solution that would both minimize their IT investment costs and facilitate remote collaboration. Onshape was chosen for its cloud-native features. We enable simultaneous editing, real-time feedback, efficient collaboration, and reduced design time were essential for maintaining productivity and meeting a whole bunch of diverse client needs globally. Onshape's cloud-native platform supports simultaneous editing, enabling real-time feedback and efficient collaboration among team members, regardless of their location. Now, Boolean refers to a set of operations that can be performed. Boolean refers to set operations that can be performed with 3D objects, adding, subtracting, intersecting, etc. Onshape has really robust Boolean operations that allow for creating complex geometries by combining, subtracting, or intersecting shapes, facilitating the development of intricate and precise micro 3D parts essential for various high-precision applications. Onshape has a unique multi-part modeling environment where it's extremely easy to split or combine geometry into single or multiple parts. Our flexibility combined with our powerful Boolean operations lends itself perfectly to NanoVoxel's process of defining regions with different resolutions. Now, all CAD has Boolean operations, but Onshape has the most powerful multi-part environment in our part studio environment. I was amazed to see the parts that NanoVoxel is able to print. Now, I've seen many 3D printing tools, and they're used extensively, and most of the time people are making larger scale parts, like parts you'd hold in your hand, or parts like a machine part, a scale of many inches or many centimeters in size. But the NanoVoxel parts get stunningly small. They even can print something that looks like a small building if you look at it under a microscope, but the size of it fits on a tip of a pencil. It's amazing. You can see it on their website. So they're doing things at such a small scale, it's almost unbelievable compared to what I'll call normal size parts that you'd see in most kinds of manufacturing. We're very proud to see NanoVoxel using Onshape, not only for the sort of traditional reasons of Onshape, the cloud native, the savings in time and money, the real-time collaboration, but also NanoVoxel appreciating the geometric modeling power of Onshape. Lets them use the part studio mode, lets them flexibly think about multi-part modeling in a way that was not possible with older parametric systems. Also, powerful Boolean operations and direct editing let them get just the precise modeling results that they need using a straightforward, clear set of modeling features.
Thanks to John for giving us an insight into Onshape, and our guest Domenico for showing us firsthand how NanoVoxel's cutting-edge 3D printing technology is transforming industries. And also thanks to our producer Aaron for taking us on the tour with him. Please rate, review, and subscribe to our bi-weekly Third Angle episodes wherever you listen to your podcasts, and follow PTC on LinkedIn and X for future episodes. This is an 1860 production for PTC. Executive producer is Jacqui Cook. Sound design and editing by Rema Mukena. Location recording by Aaron Olsacher, and music by Rowan Bishop.